lecture of this course. I'm going to wrap up most of the ideas that we've been discussing over the past 4 or 5 months. Especially, I would like to give an example today of an application of the quantum electrodynamics theory to electric circuits. And this is how most of the superconducting quantum circuits are built these days, which are also commercially available. So, we'll talk about Circuit-QED. I'm going to break up this lecture into different smaller sections. First of all, we all know that the superconductor is an exotic quantum material. Amongst its many other properties, one of the properties for a superconductor is that it has zero resistance. And such a material superconducts below a certain critical temperature. For example, for aluminum, the critical temperature is about 8 or 9 kelvins. So a superconducting circuit works as a superconductor only at very low temperatures, below the critical point. So first of all, let's try to come up with a circuit which is made up of a superconducting material, and let's call it a superconducting resonator. So today's lecture is going to evoke different concepts from electricity and magnetism as well, and electrodynamics. So consider this simple circuit, a capacitor and an inductor. Okay, so this capacitance is C and this inductance is L. So now if you look at the energy inside this system, what do you think would be the energy trapped inside this resonator? All of this is made up of superconducting material, so there is no resistance whatsoever in this circuit. It's below the critical point. So what's the energy inside the system? So what's the energy stored in the magnetic field and the energy stored in the electric field with these circuit parameters? Exactly. So the electrical energy is half Cv squared, or the charge on the capacitor divided by 2 times the capacitance plus half L I squared. So where I is the current through the inductor and Q is the charge on the capacitance. So this capacitance carries charge and some current flows through the inductor. Now we also know that a current that flows through the inductor is going to produce a flux, a magnetic flux. That flux is Li. So the energy inside the system is going to be Q squared over 2C plus 5 squared over 2L. Alright. Now if you compare this expression for the energy with a mass attached to a spring constant K. So what's the energy inside this mass spring constant? Inside this mass spring system? There's some potential energy and some kinetic energy. So what's the energy inside this mechanical oscillator? Well, right, P squared over 2m plus half m omega squared x squared. So look at these variables. There's a p here, a momentum, and a position. And look at these variables. There's a flux and a charge. So if this were a quantum mechanical circuit, say very few photons inside the system, after all this is an electromagnetic field. And so is this. And this electromagnetic field comprises of photons in the quantum mechanical sense. So this is a quantized field. circulating inside this resonator, and there are two relevant degrees of freedom for that electromagnetic field. There is a flux variable and a charge variable, and the correspondence between a mechanical oscillator is straightforward. This flux plays the role of position, charge plays the role of momentum. So in the quantum mechanical sense, if this were transformed to a quantum mechanical system, this becomes a harmonic oscillator with phi and q becoming the conjugate variables with some commutation relationship between operators for which q and phi are the eigenvalues. So if I were to promote this to a quantum mechanical version, q becomes a quantum mechanical operator, q squared over 2c is the electrical energy stored inside this electromagnetic field, and phi hat square over 2L. So this is the Hamiltonian associated with this oscillator. Okay, so far so good. So now once we have the Hamiltonian, in today's lecture we're also going to use the concept of the Lagrangian. Okay. Now this part is the potential energy part. This part is the kinetic energy part. So likewise, this part is the potential energy, and this part is the kinetic energy, the equivalent of the kinetic energy. So I can write a Lagrangian for this system, which is the kinetic energy minus the potential energy, and that will be given by q squared over 2c minus phi squared over 2L. Alright? By the way, if I were to take the Lagrangian and find the derivatives, one more thing that I can identify is that this q, another way of writing this expression is the following. This q I know is equal to C voltage. Let me write the voltage with a small v. Correct. And I know that this voltage is developed across these two terminals. And Kirchhoff's voltage law means that this voltage is going to appear across the capacitance. But the voltage is, from Faraday's law, just the rate of change of flux of the system. So this voltage can be written as d phi by dt. Correct? This is from Faraday's law. So this is C phi dot. So I can also write this Lagrangian in the alternative form. That alternative form goes as follows. The Lagrangian is half c squared, and there's a c in the denominator, c phi dot square minus phi square over 2L. And for a moment I'm dropping these the hat notation from the Lagrangian. So this is the Lagrangian. This Lagrangian is a function of phi and q, or phi and phi dot. Correct? And do remember that from the basic notions of classical mechanics, if I were to take the Lagrangian and find its derivative with respect to phi dot, then that derivative will give me c phi dot, which is nothing but the charge. Okay, and the Hamiltonian can also be derived from the Lagrangian in the following fashion. If I know the charge, the Hamiltonian is going to be equal to charge phi dot minus L. So this is something we know from classical mechanics. So we started here with the Hamiltonian. We wrote down the Lagrangian, but we could also start from the Lagrangian and write down the Hamiltonian. Alright, so far so good. So we now have the Lagrangian in front of us. What about the equation of motion for the superconducting oscillator? So suppose I want to find an equation of motion for the flux through this superconducting oscillator. So how can I find the equation of motion? The Euler-Lagrange equation. So I take the derivative of the partial derivative of the Lagrangian with respect to phi dot minus the derivative of the Lagrangian with respect to phi. Equate this to 0. It's an unconstrained system. This will give me the equation of motion for this oscillator. Okay? So it will give me the dynamics of the flux through this superconducting circuit. So if I take this Lagrangian over here and find the derivative with respect to phi dot, this will be C. The derivative with respect to time gives me a double derivative minus the derivative. Phi and phi dot are now independent variables. The derivative of L with respect to phi is phi over L is equal to 0. So this will give me the double derivative of the flux through the system is going to be equal to 1 over LC. So this is the equation of motion. And the equation of motion, when solved, will give me, with respect to time, the flux. What would that flux look like? Hypermonic. It's a second order differential equation with a constant coefficient. So it's just going to be sinusoidal function, right? So some sinusoidal function, of course, with some phase. And what's the frequency of this oscillation? 1 over under LC. 1 over LC. This is the resonant frequency of an oscillator, be it superconducting or otherwise. So now we started off with a superconducting oscillator. We wrote down the Hamiltonian. As an A side, we wrote down the Lagrangian. From the Lagrangian and the Euler equations, we were able to find out the dynamics of the flux inside the system. So far, so good.
जो डिफरेंशियल इक्वेशन है इसमें कोएफिशिएंट जो अगर फाई को दूसरी साइड में ले जाए तो 1 ओवर LC पॉजिटिव है तो एक्सपोनेंशियल
Oh, there's a negative sign, sorry. यहाँ पे तो माइनस है, यहाँ पॉजिटिव है, sorry. Sorry. All right. So now what should be, if I would like to quantize this, what should the next steps be? If I would like to further go into the quantum mechanics of the system, what do you think should the next steps be? I would like to express the Hamiltonian as a harmonic oscillator, the Hamiltonian for a harmonic oscillator. What do I need to do for that purpose? So I would like to express this Hamiltonian in terms of ladder operators. So what do I do with the position and the momentum operators normally in the second quantization formalism? I express the position and the momentum operators as superpositions of ladder operators. And I do exactly similar procedure over here. Okay, so I define my ladder operators just as I do for any harmonic oscillator problem when I'm doing a double quantization kind of arrangement. So if I would like to write down the commutation relationships, I would really, first of all, I do know that my position and momentum operators, they have a commutator I h bar. So my phi, which is the equivalent of position, and my q, which is the equivalent of momentum, should give me a similar relationship. And I do also know that the ladder operators satisfy this combination relationship. So I express my q as the sum of A and A dagger, and phi as the sum of A and A dagger, and q as a difference between A and A dagger. And with the proper coefficients, this becomes my flux operator is h bar 2 omega naught c under root A plus A dagger, and my charge operator is minus I h bar omega naught c over 2 A minus A dagger. Okay, so I just take these operators, insert them into the Hamiltonian, do all the algebraic stuff, look at the commutation relationships between the ladder operators, apply those operations as you normally do in any second quantization problem, and lo and behold, you obtain a Hamiltonian which is identical to the Hamiltonian for any harmonic oscillator. Alright, so this exactly equals this. Now we do know what the spectrum for this Hamiltonian is. It's simply a harmonic oscillator with a ground state, energy h bar omega naught 2, and equally spaced levels with a separation of h bar omega naught between any two successive levels. So if you're in the ground state, what does that physically mean with respect to the superconducting resonator? What does the ground state mean? There's no photon in the system, only vacuum. Okay, so there are 0 photons in the system, ket 0. Now this first excited state means ket 1 photon in the system. Ket 1. So if this oscillator were in the state ket 1, it means there is 1 photon in the system. Okay. That 1 photon is distributed inside the electromagnetic field inside the oscillator, and it's impossible to tell whether it's in the capacitor or it's in the inductor. Just one quantum field inside the superconducting oscillator. Likewise, you can have 2 photons, 3 photons. You can also have an arbitrary quantum state. If ket n is the number of photons, you could have a state of this kind. Any arbitrary quantum state is possible. And this is the electromagnetic field inside the oscillator, expressed in terms of photons. So far, so good. So now what we've given a quantum mechanical flavor to a simple circuit. A simple circuit is a quantum element. And I would like to see whether it's a qubit or not. Now, the problem with this circuit is that it has many levels. And it does not really qualify as a qubit because a qubit requires just 2 levels. So somehow this isotropy of levels, this homogeneity of levels has to be broken. It's a harmonic oscillator. You have to make this inharmonic. You have to give some nonlinearity to the system. Currently the potential energy is proportional to phi square. Okay? And you really need to, so is really proportional to the square of A plus A dagger. So you have to give it some non-linearity or inharmonicity to give you two levels that are distinguishable or discernible from all other levels. Okay, and that's what I'm going to show you how you can achieve that. Now, the next thing I would like to talk about, you all remember what the Jaynes-Cummings model is? So if I were to write down the Jaynes-Cummings Hamiltonian in the Schrödinger picture, what does that Hamiltonian look like? Can you spell it out for me, please? So there's a field term, a photonic term, h bar omega a dagger a. I'm ignoring the 0 point energy.
H bar omega naught over 2 Pauli
Plus something that corresponds to the atom.
sigma d
Plus a coupling term, an interaction term. H bar lambda a plus a dagger sigma minus. So this is our Jaynes-Cummings Hamiltonian. So what we have in this model is we have a photonic field, a radiation field, and a two-level atom. Okay. This photonic field is simply a harmonic oscillator. When we quantize the electromagnetic field, we got a harmonic oscillator. So now, in one sense, we have built up one part of the Jaynes-Cummings Hamiltonian. The only thing is that instead of a cavity with perfectly reflecting mirrors which traps a photon, now we have a circuit, an inductor and a capacitor intertwined to form an oscillator or a resonator that forms a cavity. So that's why this is called Circuit-QED. Alright. What we would now like to do, we would like to couple two oscillators together. So we might have an oscillator, and instead of an atom, we have another oscillator. Okay? So let's couple two oscillators together and see if we get some semblance of the Jaynes-Cummings Hamiltonian again. Okay? And remember, in the back of your mind, you do keep in mind that somehow we have to break this harmonicity. So let's couple two oscillators, coupled resonators. Remember, everything is still superconducting. All the circuit elements that we're using are superconducting. So now if I have my capacitor, inductor, and I have another replica, not an exact replica, possibly with different circuit elements, and somehow I couple them. Now, coupling can be done by different means in real circuits. So, what do you think are physical mechanisms of coupling two oscillators? दोनों की बराबर करने और पास रखने एक तरीका तो ये you just put them in close proximity with one another, and then there will be a mutual inductance between these inductors which is going to couple them together. So why don't you just place them close together? So that's not a good approach in real circuits because the mutual inductance is hard to control, and then there could be stray effects as well. So just imagine that this superconducting circuit is extremely fragile, prone to decoherence. So it's really cocooned and placed in a very isolated environment at extremely low temperatures, maybe of the order of millikelvins, inside a dilution refrigerator. So the mechanism that is normally used to couple these circuits is through a physical capacitor. Everything still is made up of superconducting material. So suppose this capacitance is CA, CB, LA, LB, and there is some coupling capacitor CG. So now we have two coupled oscillators. Now from a basic notion of physics, so your GRE physics, how many natural frequencies would the system have? If they were independent, if there was no coupling capacitor, or this coupling capacitor was absent and these circuits were far apart, then there were two independent oscillators. So there would be a frequency associated with this one over LAC and the no frequency associated with this. But now, still the number of frequencies remained. So now you have two coupled harmonic oscillators. The number of natural frequencies remains the same, but the frequencies might change because of the coupling. Okay, we've all studied normal modes in classical mechanics. So now what we could do is let's write down the Hamiltonian or the Lagrangian for the system. So there's going to be some kinetic energy and there's going to be some potential energy. Let's first write down the kinetic energy term. So the kinetic energy is coming from the charge on capacitors. So the kinetic energy is given by half Ca. Just look at this term over here. So I need the flux through capacitor A. In fact, the time derivative of that flux. So I have phi A dot square plus half Cb phi B dot square. So if the system were uncoupled, that's it. But now you have this capacitor as well. So you need the difference between these voltages. Okay, that will give me the flux. Now the voltage is the difference in these voltages is the voltage at this point will be the voltage. So suppose this is your ground terminal. The voltage at this point will be phi A dot, whereas the voltage at this point will be phi B dot, because this point is connected to this inductor over here. So this voltage will be, the difference in voltages will be phi A dot minus phi B dot. This is the voltage across this capacitor. And you convert this, you write this in terms of time derivatives of flux, and then you square, just as we've done over here. So this is the flux at this node, and this is the flux at this node, difference of voltages, and I need to put in the capacitance of the coupling capacitor. This is my kinetic energy term, expressed in terms of the time derivatives of the fluxes. Exactly in an analogous fashion to the manner in which I've written the kinetic energy over there. Now, if I were to determine the voltage, the potential energy. The potential energy, you notice, is simply given by a flux to an inductor squared. So I have two inductors, so I write down phi A square over 2LA plus phi B square over 2LB. And now I can write the Lagrangian for the system. The Lagrangian for the system will be kinetic minus the potential energy term. Okay, so let me write down the Lagrangian. The Lagrangian is half Ca phi A dot square plus half Cb phi B dot square plus half Cg phi A dot minus phi B dot. Remember, this is a difference of voltages between the nodes A and B. And you square this. So this becomes half Cb square term minus phi A to LA plus minus phi B to LB. So this is my Lagrangian.
Square. Well, potential.
Square. Okay. Now the next thing I would like to do, I would like to express this Lagrangian in terms of, and if I were to put in the Hamiltonian will simply be the sum. In the Hamiltonian, I will just write down the sum. So for completeness, let me also write down the Hamiltonian of CA phi A plus half CB phi B plus half CG phi A plus phi B plus phi A square root LA plus phi B. Alright, so this is our Hamiltonian. So now the point, so using circuit theory, by applying the Kirchhoff's voltage law, etc., we've written down what the Hamiltonian of the system is going to be. But our variables of interest are the fluxes and the charges. But the problem here, I do have the fluxes in these two terms, but here I've expressed everything as the voltages, which are rates of change of fluxes. So I would like to convert these rate of change of flux back to charge, so that I can express my Hamiltonian in terms of conjugate variables. So how can I do that?
Q is equal to C phi dot.
Sorry?
Q is equal to C phi dot. So phi dot is equal to Q divided by C.
Phi is equal to Q divided by C.
Yes, phi dot.
So what about using this relationship over here?
जैसे C की बात करें.
So what I could do, I could take the Lagrangian and differentiate this with respect to phi A dot. I will get QA. Alright. So let's do this. So I take this Lagrangian and find its derivative with respect to phi A dot. So I will get CA phi A dot. This is 0. Here I will get CG phi A dot minus phi B dot. The derivative of this is 1, that's it. So this is my QA. Correct? This is my QA. Likewise, I can find QB. And then I can write down an equation that a basis transformation, a transformation equation that connects QA with phi A dot and phi B. So if I were to repeat this calculation, find out QB. My QB is the derivative of the Lagrangian to phi B dot. This is CB phi B dot, CG phi A dot minus phi B dot minus sin A. Okay. So let me write this as a matrix equation QA QB in terms of phi A dot and phi B dot. So QA is CA plus CG, CA plus CG here, and that would be minus CG. QB is minus CG and CB plus CG. So this is my transformation equation. But I really need to go the other way. So I need to go from the derivatives, the time derivatives of the flux, to the charge. So I just take the inverse of this equation. Okay, so the inverse of this equation would let me express phi A dot, phi B dot in terms of the charges. So here I will get D is the derivative of this thing, and here I get CA plus CG or CB plus CG, correct? CB plus CG, CA plus CG. So adjoint ऐसे ही होता है.
प्लस नहीं हो जाएगी
दोनों प्लस हो जाते हैं और पहले में
नॉन
So this is my transformation from the charge to the time derivative of the flux. So I take these time derivatives of the fluxes, put it inside the Hamiltonian. Okay, simple substitution. In the end, I'll be able to write down the Hamiltonian for these coupled oscillators in terms of charges, QA, QB, and the phis. So if I were to do that, it's a lengthy calculation. So it's a lengthy calculation. Please kind of attempt this on your own. I have 1/2 1 over d square we then write on the final result. QA square over 2CA prime. This is not, I'll define what CA prime is, plus QB square 2CB prime. Okay, plus phi, nothing happens to these terms, phi over 2LA plus phi B over 2LB. But the one thing that you observe is that there's also a coupling term, and that coupling term gives me a product of these charge operators, 2 times CAB, where CA prime is given by D over CA plus CG, CB prime is given by D over CB plus CG, and CAB is given by D over CG. Right? So this is merely a basis transformation. We wrote down the Hamiltonian in terms of the fluxes and the time derivatives of the fluxes. And then we transformed to the charge degrees of freedom. So if this term were absent, then everything would be nice and easy. You had 2 independent oscillators.
So आपके दो टेबल में phi B square आएगा?
Square actually. D is the determinant. CA, CB plus CA, CG plus CB, CG. That's the determinant of that matrix. Okay? Yeah. Alright, so now this is our Hamiltonian. So far so good. So if you look at the first and the fourth term, if I were to lump them together, doesn't the first and the fourth term together look like a bare single oscillator with a different capacitance and a different with a different capacitance? Okay. Likewise, the second and the fourth term also look like a harmonic oscillator. So if I were to lump the first and the fourth term and the second and the third term individually, I'll get two harmonic oscillators. So the first and the fourth term would give me h bar some omega a. In fact, omega, let me call it omega a prime, because omega a prime is not equal to 1 over square root LACA. Right? It depends upon CA prime and LA. And CA prime is given by this modified expression. So when two oscillators are coupled, the normal frequencies change. So I have h bar omega a prime, a dagger a plus half. This is one oscillator. And then for the second oscillator, I have h bar omega b prime, a b dagger a b plus half. And then if I were to look at this term, each one of these terms is a minus a dagger. So I have a minus a dagger for both oscillators a and b. And if I were to do the proper coefficients with this will give me, let me lump everything together, call it G. Now G is some function of these capacitances, which you can work out, just algebra. And then I have a minus a dagger, a b minus a b dagger. Alright? Now, is a further simplification possible to this?
Yes.
Can I go to the interaction frame, then to the rotating wave approximation, and come back to the Schrodinger frame? So if I were to do that, A would couple just with AB dagger, and A dagger would couple with AB.
Yes.
So my overall Hamiltonian for this coupled system will be h bar omega a prime, A dagger A half plus h bar omega b prime AB dagger AB plus half, I think, minus h bar G AB dagger plus A dagger AB. Okay. This is exactly isomorphic. Not isomorphic, it's similar to the Jaynes-Cummings Hamiltonian, only that now we are coupling between two harmonic oscillators instead of harmonic oscillator and an atom. So this can be considered to be an extension of the Jaynes-Cummings model. Okay.
सर
Yes.
तो वहाँ पे तो आपके पास सिग्मा प्लस है, वो तो एक 2/2 का मैट्रिक्स है.
Here we have a field operator and an atom because we have a field and an atom. Now we have two fields. We have two bosonic fields, two harmonic oscillators, and we are coupling the two together. G. Sorry. So what we could do, if you make this time, if you go to the interaction frame, the interaction frame will get rid of these terms because these are free Hamiltonians. And this AA will be replaced by this AA will be replaced by AA exponent minus I omega A prime T. Okay. Its A dagger will be replaced by A dagger E plus I omega A prime T. And likewise for B. Okay? So now when I multiply the two together, I'll get terms of this kind. E minus I omega A prime minus omega B prime T plus minus. So I keep these terms because now I have the difference in frequencies. And these are slowly varying terms, so I keep them. But I'll also get terms of this kind. which are moving at almost double the frequency if these two gaps are almost the same. So I ignore those terms. Okay, and it also makes sense. You can also look at this from the perspective of conservation of energy. So this is the annihilation of a photon in the first oscillator, and then the creation of a photon in the other. Annihilation in the second one and creation in the. So really, it's a photon that can toggle between the two oscillators. What does this remind you of? This process of toggling of a photon from one oscillator to another, or the toggling of a photon between an atom and a field.
Absorption and emission.
Okay, so it's called the Rabi flopping. So now we have Rabi flopping between two harmonic oscillators. So far we still don't have a qubit, because we haven't broken the harmonicity. But now we have two harmonic oscillators and we can achieve Rabi flopping between the two oscillators. So somehow if I cooled this system, so that both the oscillators are in the ground state, both the resonators are in the ground state, and then I increase the temperatures a little bit, such that only one photon is created in this system. The temperature is only big enough to create one photon, or one photon is injected into the system, or one photon is being shared between the two oscillators. Then what's going to happen, that photon will belong to both oscillators. In a sense, the photon will be shared between the two oscillators. So I can also explicitly derive how Rabi flopping works in the system. So if I have a state, two kinds of states, I have one photon in the system. So one possibility is that one photon is in the oscillator A and none in the oscillator B. The other possibility is that none in A and that photon is in B. Then I have a superposition. Let's call this CA. Let's call this CB. Right? So this, suppose, is my quantum state at time t equals 0. Okay. Suppose now what I could do is, so this is this quantum state at any time. It has to be this state. There are only two possibilities. The photon is in either of the oscillators. Okay. At time t equals 0, suppose I started off with Ca equals 1 and I just had this state. So that's my initial condition. So my initial condition is psi at t equals 0 is simply, let me write this in shorthand as 1, 0. These two, of course, are orthogonal states. We're using the photon occupation number representation here. Now if I were to look, I do know what the quantum state is, and I do know what the Hamiltonian is. And I can solve this problem explicitly in the interaction representation. In the interaction representation, my Hamiltonian, the first two terms will just wither away in the interaction thing. So I'll be left with minus h bar g a perhaps e plus or minus, doesn't matter. Where this is omega a, delta is omega a prime minus omega b prime. It's a difference in frequency, in the nominal frequencies between the two oscillators. Plus a dagger, AB, E plus I, delta T. So I take this Hamiltonian and use the time-dependent Schrödinger equation. Right? I know what the time-dependent Schrödinger equation is, so I take I h bar d by dt of this Hamiltonian that I've written over here keeping in mind that these coefficients are time dependent. Okay. So these coefficients are time dependent. I find this derivative. Everything is in the interaction representation, so I put a tilde over this state, h bar. Okay, so I solve this equation. I will get a differential equation for CA and a differential equation for CB.
सर हम इसमें पार्टिकुलर
क्योंकि हम इंटरेक्शन फ्रेम में चलेंगे,
सब वो उसमें हम सैंडविच नहीं करते
सैंडविच करेंगे ना, तो ये एक ऑसिलेटर इसकी फ्रीक्वेंसी ओमेगा ए की फ्रीक्वेंसी से जो फ्रेम में जो इंटरेक्शन में जो आप ट्रांसफॉर्म कर रहे हैं दैट इज द फ्रीक्वेंसी ओमेगा ए, so this term goes away. Likewise, this term will go away. Okay. So now you can derive the Rabi frequencies. The Rabi frequencies will be proportional to G and will be proportional to G. So if I were to solve all of this, and I've done this, in fact, my CAT will be EI delta T over 2 with the initial conditions that I have. I will get 2 iota G sine of GT when I'm on resonance. On resonance, so let me first write down the expression of resonance. A plus I delta square plus 4G square over 2T plus B E minus I delta square plus 4G square over 2T. Right? So this is the solution for the Schrödinger equation. Delta is my G tuning factor. That's the difference in frequencies between the two oscillators. And G is the strength of the coupling between the two oscillators. Depends on the capacitances. If my delta is 0, I have two perfectly matched oscillators. Then my Rabi frequency will be the on-resonant Rabi frequency, and that will be proportional to G. Okay, because this will go away, I'll get 2G, I'll get a frequency G. Okay, so far so good. So I can get Rabi floating between two quantized circuits. Now I'm left with 20 minutes. So the last part of this course would be, of this class would be to really somehow break the harmonicity. So I really want a qubit. In all of these expressions, I still don't have a qubit. What at best I have are two harmonic oscillators. No doubt they are quantized systems, but I have two baths of photons that are coupled with one another. An exchange of energy is possible between the two oscillators. So the photon, just imagine how beautiful this is, because just imagine that a single photon could be in a system, this vacuum here, the vacuum field here, and instead of spontaneous emission that we saw in a cavity, now we have the exchange of a photon between one circuit and the other. Okay, so this is like the equivalent of spontaneous emission or vacuum Rabi oscillations. Okay, this cannot be explained classically. No such analog exists to this in the classical world. So now how do we break the harmonicity? Somehow we need to introduce a non-linear term in the harmonic oscillator. So what we really do is the following in a real circuit. So might have a conventional superconducting oscillator. And to this we couple another system. And this time our system comprises, this is our system. This is a conventional superconducting oscillator. Could also be a transmission line. So I could replace this oscillator by a transmission line, like a waveguide. Capacitor. The only thing that I do have now is this circuit. I put a cross here. Now this object here is a Josephson junction. What is a Josephson junction? A Josephson junction is, this represents a Josephson junction. Josephson was the physicist who in his PhD wrote down the Josephson equations. So it's a piece of superconductor, another piece of a superconductor, and in between there is a layer of an insulating material. Okay. So this, for example, could be aluminum superconductor. This could be any insulator, say aluminum oxide. This could be niobium tin, niobium oxide, or any other oscillator. And all of this is epitaxial, so it's one crystal structure. And everything is at superconducting temperature. So this junction between two superconductors, separated out by an insulating barrier, is called a Josephson junction. So this object here is a Josephson junction. This is the junction capacitance, the capacitance associated with the Josephson junction, Cj. So this is some capacitance. It's a very small capacitance, femtofarads perhaps. And this is a Josephson junction. Now we need to look at the quantum mechanical description of this Josephson junction. And the Josephson equations were derived in the 1950s. And Josephson won the Nobel Prize for looking at or deriving the equation, the two equations for the DC Josephson effect. So in order to understand superconductors, it's a totally different change from our normal physics. So, and it would require a lot of time, in fact. So let me see what I will need to. First of all, just have 15 minutes. So let me give you the scheme of the quantum mechanical version of this circuit. First of all, I need you to know that flux is quantized. Does everyone know why flux is quantized, and does everyone know about this? फ्लक्स की क्वांटाइजेशन का मैग्नेटिक फ्लक्स की क्वांटाइजेशन पढ़ा है किसी कोर्स में? मैग्नेटिज्म में पढ़ा है. Alright, so if I have a superconductor, I can write a waveform. The property of a superconductor is, so if I'm inside this material, the electrons, in fact pairs of electrons are paired together in the form of Cooper pairs, and they have a giant wave function, some one big wave function, just like photons coming out of a laser. So all of those fermions that are contributing to superconductor are described by a big wave function, a macroscopic wave function. That macroscopic wave function, let me write, you know this as psi. This is, the modulus square of this is the number density of Cooper pairs. So the magnitude will be, let's approximate this as the square root of the number density of Cooper pairs, and some phase. Okay, so this is the wave function, the macroscopic wave function of a superconductor. Okay? Theta is called the order parameter. So if I take the momentum of this state, this will be square root n I ei theta. Correct? This will be the this is the momentum operator acting on the wave function. Okay. So now what I could do is iota. Oh, there's a minus iota h bar. And minus iota h bar. So this is h bar square correct? So the momentum of this giant wave function is simply h bar del of theta. Alright. Now suppose I take a superconducting material. This is my superconducting material, a giant blob of superconducting material. And inside this material I make a hole. So this is vacuum here. All of this is vacuum. Now I draw a closed loop around this hole. Okay. This is a contour, a closed contour, and I take the line integral of the momentum across this, along this contour. Okay, so this is my line integral. This is my momentum of the fermionic pairs, of the Cooper pairs. So this becomes h bar. This is a line integral of a gradient. So this will simply give me h bar, and since it's a closed integral, this will give me phi a minus phi b, where a and b are both the same points because I'm moving around a closed loop. So now the wave function has to be unique, which means that this phi a minus phi b has to be some multiple of 2 pi. So I'll get h bar 2 pi n, okay, which is h n. Now I also know that the momentum, what's the definition for momentum? It's mv. But what about when you're talking about electromagnetic fields as well? It's the canonical moment, the momentum is replaced by the canonical momentum. So it will also depend upon the magnetic vector potential. So Cooper pair, which is 2 times the mass of the electron, the velocity of the Cooper pair, plus the charge on the Cooper pair, which is minus 2e magnetic vector potential. Okay? Now this term corresponds to current density. Remember from your electricity and magnetism course, the current density is given by, if you're talking about normal electron, J equals n q or e p, right? So this term is proportional to current flowing inside the superconductor. But we assume that there is no current inside the superconductor. There is no current inside the superconductor. There could be flux through the system, and that flux is inside the hole. For a superconductor, no flux can penetrate this in the interior of the superconductor because circulating currents are produced. which oppose the flux according to Lenz's law. In fact, this is called the Meissner effect. So there will be no flux inside the conductor, only flux through the hole, which means circulating currents are produced just on the inner periphery, and there will be some skin depth over which currents will produce, but we assume that our contour is far away from that skin depth. So there is no current inside the superconductor. So for our case, this term is 0. So now if I were to take P dot dl, with this definition over this closed loop, I get minus 2E A dot dl. But what is A? How is A related to the magnetic field? A is the magnetic vector potential. What is B? B is del cross A. It's the curl of A. So what I could do is I could use the theorem del cross A. I take the curl of this A, the dot product over the surface, and convert this closed integral into a line integral into surface integral. This is called the Stokes theorem. But this del cross A is B. So B dot ds is the flux through the hole. So this is minus 2E flux. But this equals Hn. So the flux, the magnitude of the flux is n times h over 2E, given some n. So the flux could be h over 2E, 2h over 2E, 3h over 2E. Only these discrete values of flux are possible inside this hole punctured in a superconductor. So the flux becomes quantized. This is a unit of flux, it's called the fluxon. Okay? The flux is quantized in the quantum mechanical world, just like the charge is quantized. Now, charge and flux should be on equal footing because both of them are conjugate variables in the Circuit-QED model. So now what we could do is a long lengthy calculation. We need to derive the DC-Josephson equations. So if let me give you the very basics of the DC-Josephson effect. So if I have two superconductors sandwiched by an insulating material, and I have some voltage here and I have some voltage here. This is my superconductor 1, superconducting 2. There is going to be some wave function here, n1 ei theta 1. There is going to be some wave function here, n2 ei theta 2. Okay. There is going to be some energy here. Suppose this voltage here is V over 2, this voltage is minus V over 2. Okay. So there will be some energy here and some energy here. And Cooper pairs in superconductor 1 can tunnel across the barrier and reach the metal 2, reach the superconductor 2. So one can write differential equations for the wave functions. So let me just show you how those differential equations are written. Simply the time-independent Schrödinger equation iota h bar d by dt of psi 1. Let's not write these ket here. This equals the energy inside this system. Now the energy here is going to be some basic ground state energy U naught plus V over 2 voltage times the charge of the Cooper pair, which is 2E. So I'll get u naught plus EV psi 1, right, for this part. But there's a possibility of tunneling of the wave function psi 1 and psi 2. So I need to include some term that takes into account tunneling. Let's call that term kappa. That's a coefficient kappa. Likewise, I can write a differential equation for the wave function in this superconducting part. So this will be u naught minus EV psi 2 plus kappa psi 1. Now I have these two differential equations and I can solve them as I treat simultaneous equations. So I'll get some solutions. So the solutions to these equations are the DC-Josephson equations. And the two equations that I do get are the following. Which is the current coming out of superconductor 1 and entering the insulating barrier. This current is I1. This I1 is some critical current sine of theta, where theta is defined as theta 1 minus theta 2. Now, I'll give you my handwritten notes on how to derive these equations. And the second equation that I get is this P equals phi naught, which is the fluxon over 2 pi theta dot. So these are the two equations that I finally get. Okay. These are called the DC-Josephson equations. Now, if I differentiate dI1 with respect to time, I will get IC cosine theta d theta by dt, which is now 2 pi over b phi naught. Sorry. 2 pi. Okay. Alright. So this means that my voltage is phi naught over 2 pi IC. Let me write cosine theta. This cosine theta, let me write this as 1 minus sine theta square root. 1 minus, but my sine theta is I1 over IC. So the one step that I've missed, but that's just algebra, is starting from this pair of equations, I can derive these DC-Josephson equations. That's the only step that I've missed. This is purely algebra. Okay. So please try to attempt this. I'll probably give this in as one of the homework problems. So now when I have these expressions, I merely take the derivative of this d1, but I will show you something. So this is the derivative of I1 with respect to time, and I juxtapose the variables such that I have V equals some lump parameter gi 1 by gt. Now what does this look like? This is like an effective, so if you recall your circuit theory, if my voltage is proportional to the time derivative of the current, what kind of element is this? So my current changes rapidly, the voltage across that element builds up. What is that element called? You're physicists. What is such an element which produces a voltage across it whenever the current changes through it? क्या होती है ये element? कौन सा element है? Capacitor. नहीं. Inductor, it's an inductor. Because a changing current changes the flux. That flux is proportional to the voltage. It's a Faraday law at work here. So this object here is like an effective inductance. L, some effective inductance, which is now somehow quantized because this is phi naught or 2 pi IC, depends upon the parameters of the junction. And this is now dependent on the current through the system. So the inductor, and linear inductor is one which does not depend upon the current through it. Linear capacitor is one which does not depend upon the voltage across it. But this is now a non-linear inductor. This non-linear inductor breaks the harmonicity of the harmonic oscillator. And in fact, this is how we achieve a harmonic oscillator which is inharmonic, in which all the levels are differently spaced. And you can do a calculation for this purpose as well. You can write the Hamiltonian for. So what the next step that you need to do is to take this junction, Josephson junction, in parallel with the capacitance, write the Kirchhoff's voltage law for this, find out the kinetic energy of the system, find out the potential energy of the system, write down the Lagrangian for the system, find out the conjugate variables, the flux and the charge, write down the Hamiltonian for the system, and employ the second quantization formalism to see what the eigenstates of the system are. This is your, let me just write down the Hamiltonian. The Hamiltonian is very interesting. And I'll share my handwritten notes for this as well. The Hamiltonian for this system is given by this really nice form. Eventually, after I do all my calculations, minus Ej plus H bar omega naught, and I'll define what omega naught is. Ladder operator C dagger C plus half minus EC over 12 C plus C dagger raised to power 4. Okay, where omega naught, this term omega naught is 2 pi IC E Cj H square root, and EC is some combination of capacitances. EC is in fact the energy that is required to produce a Cooper pair, which is E square over 2C. Okay, E square over 2C. That's the energy that is required to produce a Cooper pair in an object of capacitance C. That's called the charging energy. Ej depends somehow on the critical current and so on. So this is our Hamiltonian. After this course, you should be able to derive this Hamiltonian from the DC Josephson equations, and I'll frame a homework problem around this. So if you look at this Hamiltonian, this is the Hamiltonian for this object. This object, by the way, is called a transmon. This is your qubit. So look at this transmon. This transmon is coupled to some waveguide, some transmission line, or another harmonic oscillator, or a resonator. If you didn't have this term, nothing would change. You still have a harmonic oscillator. But now the addition of this term creates inharmonicity in the system. And if I expand C plus C dagger and deploy the commutation rules for the ladder operators, I can simplify this. I will keep only those terms in this fourth power, which have equal number of C's and C daggers, because I want to respect energy conservation. And when I'm able to do that, I can find out the eigen energies corresponding to this Hamiltonian. And now the harmonic oscillator, which was a nice parabolic function, due to this quartic term, this is a quartic term, it kind of changes its form. And the harmonic oscillator levels are no longer equally spaced. In fact, you can derive what the spectrum associated with these levels is going to be. And so there will be the first two levels at some spacing, the second and third levels will have a different spacing, the third and fourth levels will have a different spacing, and so on. Okay? So please expand this quartic potential and find out the spectrum for this modified harmonic oscillator, this inharmonic oscillator. Now you can use, since there is a precise gap between any two levels, you can use any two of the levels inside this manifold of energy levels to function as a qubit. So at the very end, this is your qubit over here. This is our qubit, the transmon. And this capacitance and inductance inside the superconducting oscillator are such that its natural frequency matches your desired frequency. And for this now acts like an atom, in fact, because you just have two levels inside the inharmonic oscillator. So this is an atom, and you recover the full form of the Jaynes-Cummings Hamiltonian for atom-free interactions. This now becomes a two-level atom, or a qubit, and this is how the transmon works. Alright, so I'll frame some questions, just one question so that you can complete the derivations for this transmon. So inshallah your exam is on Tuesday. So I'll upload the last homework.